All right, so we're going to finish out our colligative properties this morning. And we're going to basically, we've got three things to discuss: um, freezing point depression, boiling point elevation, and a third concept of osmotic pressure. And when we do that, I'll kind of close out the first half of this, kind of cumbersome chapter, and really more like the first 2/3 almost. And then when we come back from the break, we'll start talking about solids, which is something a little bit different, um, before we break in and do some getting ready for tomorrow's test. So we brought on this idea yesterday that because of the increase of intermolecular forces, solvents, liquids, tend to want to stay in the liquid phase if we introduce solutes to them that increase the number of intermolecular forces and therefore increase their ability to stay in that liquid medium. And so we see a shifting of phase boundaries as a result of this, and we call it by two different names. On the high side of the temperature scale, we have boiling point elevation, where solutions will boil at temperatures higher than expected, higher than the normal boiling point for the solvent, because of the increase in intermolecular force. And we also see freezing point depression on the other side, where liquids will freeze at lower temperatures than the pure solvent will on its own, because again, the increase in intermolecular forces causes you to have an increase in the ability of a liquid to stay a liquid, and therefore it's going to be a liquid over longer temperatures and temperature ranges. So if you remember back to phase diagrams in Chem 105, what we see effectively is the dark lines in that phase diagram represent the normal boundaries of solid, liquid, and gas. The dashed lines represent the new boundaries of that solution. So we can see that the new boundary that exists is going to make the overall temperatures at which something freezes lower, and the overall temperatures when something boils higher as a result. Now, the values of Kf and Kb, those are constants, and they are specific to the individual solvent. So the solvent itself is what dictates Kf or Kb, and it has a lot to do with the intermolecular forces that are exhibited by that particular solvent. So let's take a look at a couple of example calculations that you could do. First one, we're looking at cinnamon and cinnamaldehyde. So the primary flavor component in cinnamon is a compound known as cinnamaldehyde. What we want to do is we want to determine the boiling point elevation of a solution of 100 milligrams of cinnamaldehyde that's dissolved in 1 gram of carbon tetrachloride. So the calculation here is delta T B, the boiling point elevation, is equal to Kb times the molality. Now, Kb, we already know, 2.34 degrees Celsius per molal. That's the value for carbon tetrachloride, the solvent. We need to figure out the molality. For molality, we need moles of cinnamaldehyde divided by kilograms of solvent, which would be the carbon tet, CCl4. Now for that, we're going to have to do a little bit of extra calculation because we can see that we only have a mass, 100 milligrams. We don't have a molar mass yet. We certainly don't have moles. So 100 milligrams is 0.1 grams of cinnamaldehyde, C9H8O. And we want to turn that grams into moles. So we need the periodic table. Carbon is 12.01, and there are 9 of them. Hydrogen is 1.01, and there are 8 of them. And oxygen is 16. So the mass here is 132.17. So if we take that, 0.1 divided by 132.17 to 3 significant figures, 7.57 times 10 to the negative 4th moles of cinnamaldehyde. So now we can calculate our molality. 7.57 times 10 to the negative 4th moles divided by 0.001 kilograms of solvent. Our molality is 0.757 molal cinnamaldehyde. So if I put that value now into my boiling point elevation, I see that my molality calculation is going to cancel out as a unit, and my boiling point elevation is going to be 2.34 multiplied by 0.757, which to 3 significant figures would be 1.77 degrees Celsius. Now, one really important thing about this calculation. This is a calculation that is only telling us how much the boiling point changed. It's not the actual boiling point itself. Carbon tetrachloride does not boil at 1.77 degrees Celsius. If it did, we'd have a different name for it. Gas. Carbon tetrachloride is naturally a liquid. So if the question were asking us, well, what is the boiling point of this solution? We would have to look up what the boiling point of carbon tet is and add this 1.77 to it. All right, questions here, questions so far? Okay, so before we open this one up, let's just make sure we grab the important piece of information off of the information table. So KF for water is 1.86 degrees Celsius per molal. So we have 0.2 moles of glucose added to 200 grams of water. what temperature does the resulting solution freeze? Freezing point depression calculation equation is effectively the same as what was for boiling point. It's the constant times molality. We have the constant, we just need to figure out the molality. All right, question here. The number is set up very, very easily for us. We need to find the molality. So we need moles of glucose divided by kilograms of water. They've been kind enough to give us the moles of glucose. 200 grams is 0.2 kilograms. And so 0.2 divided by 0.2 would be 1.00 molal glucose solution. Plugging into our freezing point depression, then 1.86 degrees Celsius per molal times 1 molal degree Celsius would be left over. We get a 1.86 degrees Celsius. Okay. Now, the thing that we want to watch out for, because our answers, like any good multiple choice test writer, the answer that we get directly out of the equation is one of the options. And sometimes that is the correct idea, and sometimes it's not. So, our split here, we have to look out for a couple of things. The normal freezing point of water is 0. But we've calculated a change to that freezing point. The change to that freezing point is 1.86 degrees. Now, the question we have to ask ourselves is, are we going 1.86 degrees above 0, or are we going 1.86 degrees below 0? And what we have to remind ourselves is, well, what is it that we just calculated? We just calculated the freezing point depression. Depression would mean that we are going down. So we've got to subtract. So what does that look like? Well, it looks like our freezing point would be 0 degrees for water minus the change that we just calculated, which would be negative 1.86 degrees Celsius. And so that's why that the last question, the last answer here, is ultimately the correct answer. It's correct because we've got to go down in temperature there. All right, let's switch gears and start talking about osmotic pressure. So osmotic pressure is related to the process of osmosis. Now, you've heard about osmosis. All of you in this classroom, everyone who's listening to this in perpetuity took biology at some point in their lives and learned about osmosis in biology. It's the idea of water traveling across a medium from an area of high concentration to low concentration. Happens in your cells all the time. Happens in a number of other places as well. Now, there's some terminology that gets brought in here that your book's bringing in. The idea of hypotonic solutions and hypertonic solutions. Just fancy ways of saying high concentration, hypertonic, low concentration, hypotonic. And if they're even concentrations, well, that would be the term in the middle, isotonic, meaning same concentration. Iso means same. So in a situation like this, you'll see a natural progression of water molecules passing from the lower concentration side to the higher concentration side in an effort to try to get the two solutions to come to an equilibrium of concentration. And so what will happen over time, if we let it, is that we'll get something like this, where one side of this U tube is distinctively higher than the other side of the U tube. And we can measure that difference. So that difference in height between the two areas, the two zones there, that marks a value that we can measure and ultimately calculate a force based on gravity and height and whatnot. Now, if we apply a pressure to get it back to the original state so that delta H goes back to being 0, the pressure that we would apply is the osmotic pressure. That is the pressure that is basically being exerted through the movement of that water. So by definition, osmotic pressure is the pressure that we apply to a separated solution to stop the flow of the water. We can calculate its value using 3 different parameters. Capital M, the molarity, R, the universal gas constant, and T, the absolute temperature in Kelvin. Now, the question is, well, what value of R do we use here? Really just depends on what pressure unit we want for our osmotic pressure. Usually this breaks down into the most common 2 pressure units. If we're using torr or millimeters of mercury, the R value that starts with 62.36 and has all the units on it would be the one that we use. If we're looking for atmospheres, 0.0821 is the one that we would use. It would be a very odd, rare circumstance that we would use something like 8.314 in this context, because I believe that one goes to kilopascals or something along those lines, which we almost never use in chemistry. So let's take a look at a couple of practice calculations that we can do with these. So let's say that the total concentration of solute particles inside of a red blood cell is 0.310 molar. What is the osmotic pressure of that blood fluid at normal body temperature 37 Celsius? As you should know from biology, the membranes surrounding these cells in your body are semi-permeable, meaning water can flow in and out of them. So using the equation, osmotic pressure pi is equal to capital M times R times T. Our molarity is 0.310 molar. Our R value, since we have not been given anything specific, I'm going to just default to atmospheres here. And 37 Celsius, 37 plus 273 is 310 Kelvin. So how does the unit cancellation work here? Well, we can see that Kelvin in the numerator, Kelvin in the denominator, that one cancels out pretty easily. How does the molar cancel out here? Well, we have to remember that molarity is moles over liters. And so we can see that it's matching pair in the R value. Moles in the numerator here, but in the denominator here, they're going to cancel. Liters in the denominator here, but in the numerator here, they're going to cancel. All that's going to be left is atmospheres, which is a pressure unit. And since this is called osmotic pressure, we better come out of this with a pressure unit. So 0.310 times 0.0821 times 310 to three significant figures, 7.89 atmospheres. So one of the things that we will notice about osmotic pressure is that osmotic pressure generates a pretty decent pressure value. I mean, this is almost 8 times greater than atmospheric pressure. And it does so without having us to really resort to super high temperatures. I mean, 37 degrees is your body temperature. So, 98.6 degrees Celsius, not the greatest day outside, but not exactly, not nearly the same thing as 500 Kelvin. And it also doesn't require extremely high concentrations either. This is just a 0.3 molar solution, and we're getting really high, noticeable pressure values. All right, questions with this one? All right, let's take a look at another top hat question here. Rank these solutions in order of highest to lowest osmotic pressure. And you got 5 different options here. So since all these are assumed to be at the same temperature, this really comes down to a question of concentration. Which one of these has the greatest concentration? Which one of these has the least? So the thing about questions like these is there's often a lot more here than what meets the eye. And so notice that we aren't being asked to actually calculate the osmotic pressure of any of them. We're really only being asked to rank their osmotic pressures against each other. And like I said, since we're assuming they're at the same temperature, and we know that they're the same solute and the same solvent. Really, all that matters is the concentration itself. And since we're given everything in terms of grams and liters, the easiest way to solve this problem is just to figure out which one has the most glucose in it. And the way to do that is to standardize it. So I look at this and say, okay, I've got 1,000 milliliters here and 1 liter here. So let's just bring everything up to that level, and we'll be able to make a direct comparison. So for this first one, we have 3 grams in 100. Well, if it was 1,000, so multiply everything by 10, it would be 30 grams in 1,000. And this one is 5 grams in 0.2 liters. Well, if we multiply it by 5, it would be 25 grams in 1 liter. This one's already in a liter. This one's 500, so if I multiply it by 2, I would have 50 grams in a liter. This one's already in a liter as well. So now I have an even playing field for comparison. So ranking these in order from highest to lowest, this fourth one is the most concentrated, so it would have the highest osmotic pressure. Next in line would be this one, followed by this one, then this one, and then finally the 10 grams and 1,000 would be the least concentrated and therefore have the least osmotic pressure. So this question wasn't even really about osmotic pressure so much as it was about concentration and ranking concentrations. Right. Any questions with osmotic pressure before we go further? Okay, so there's one thing that we've been kind of leaving off to the side here. Almost everything that we've been doing up until this point has largely focused on, well, what if I have something that is non-electrolytic? If I have strong electrolyte solutions, what I see is that the electrolyte solution tends to have a greater impact on freezing point and melting point and so on. And the primary reason behind that has to do with entropy. When ionic compounds dissolve in water, they break apart into more particles. And as we know, more particles means more entropy. More entropy means more mixing. We're also going to see greater intermolecular forces because we have more particles to do intermolecular forces with. So even just a simple example like this, where we've got freezing water at equilibrium. And we'll notice that in pure water, the value is 0 degrees. In glucose, it drops down to negative 1.86 degrees. In the sodium chloride, it drops down to negative 3.54 degrees. Even though the concentrations are the same, we see that the impact is not the same. So what's going on here? Well, One of the explanations for what's going on is something called the Debye-Huckel theory. And what the Debye-Huckel theory kind of predicates on is the idea that, well, when sodium chloride dissolves in water, it's not giving us one particle, it's giving us two. So theoretically, the impact on the freezing point should be double what we expect because we're getting two particles instead of one. So if the impact is 1.86 degrees for a 1 molal solution, then we should be expecting something more like 3.72 degrees instead. That's what Huckel theory focuses on. But what we see is that this isn't always exactly the case. There's a phenomenon known as ionic atmospheres where basically, especially as the concentration gets higher, we see these kind of reformed pairs taking place. Not reformed pairs in the sense that they're making an ionic crystal and reforming the solid. Not that, but just the idea that there is a closer association with the ions than maybe we were expecting under Huckel theory. And so this is where the Van Hoff factor comes in. And we've said Van Hoff's name a lot this semester. It's come into 3 of our units now. Well, what does the Van Hoff factor account for in this case? Well, what it really gets into is it's a calculation for how to account for the difference between Huckel theory and observation. And we measure Van Hoff factor and abbreviate it with the letter I. Now, your book talks about how there is a Van Hoff factor for vapor pressure in Raoult's law. We don't tend to see that as much or talk about that as much. It does exist, but we tend to, most of the time when we are talking about Raoult's law and vapor pressure manipulation, we're usually looking at other volatile substances mixing with water or mixing with each other. And so the Van Hoff factor usually does not apply just because we don't use it as often with strong electrolyte solutions. But for freezing point depression, boiling point elevation, and osmotic pressure, the 3 colligative properties that we just discussed, it does have a very significant impact. Now, here's the thing that I need you to understand. The value of I is not something that you need to know off of the top of your head. If we are get into I kind of calculations, I want you to do one of two things. If the value is given to you, use it. So if we say you've got a solution of aluminum chloride, Van Hoff factor for aluminum chloride is 3.17, you use the 3.17 as I in whatever the calculation is that you need to do. But if it is not given to you, that doesn't mean that you just ignore that it exists. What we want you to do instead is we want you to apply Huckel theory. So in that context, what we would say in that same example is, okay, you're dealing with a solution of aluminum chloride. Well, you know that it's going to break apart. If we're not given a Van Hoff factor, we need to substitute 4 in for I, because that's what Huckel theory would suggest. Aluminum chloride would break into 1 aluminum and 3 chlorides. That's a total of 4 particles. So here are some common Van Hoff factors. Now, these are measured in 0.05 molal solution. Understand that Van Hoff factor does change with concentration. So again, rely on either the problem to give you the exact value or default to the expected, the Huckel theory. So this expected would be Huckel, and I spelled that wrong. And then this would be the Van Hoff value. All right, so let's take a look at another top hat exercise here then. Match the expected ideal Van Hoff factor to the solute in an aqueous solution. And so the expected ideal Van Hoff factor, that would be the Huckel theory expectation. How many particles does this ion, the compound, how many particles does this substance break apart into when we dissolve it in water? Okay, so this should be relatively straightforward. So molecular compounds like glucose, they do not break apart in water. Their ideal Van Hoff factor by Huckel theory would be 1 because they don't break apart. For KCl, we expect it to break apart into the potassium ion and the chloride ion. That's 2 ions in total, so that makes it match up to 2. For sodium sulfate, 2 sodium ions and 1 sulfate ion is a total of 3. So we would expect it to branch over to 3. We talked about aluminum chloride already, 1 aluminum, 3 chlorines, so 4 total. And then for iron 3 sulfate, 2 iron 3 ions, 3 sulfate ions would be a total of 5. And so again, this is theoretical. And especially when we get to, again, higher ion concentrations, we deviate further and further from Huckel, and we have to rely more and more on the experimental Van Hoffs. But again, I tell you, if you come across a problem and it does not explicitly give you the corrected Van Hoff factor, you can presume the ideal one is accurate, or at least accurate enough, and use just the what Huckel theory would predict. Now, one kind of interesting application that we have for things like osmotic pressure is that because of that really easy ability to measure molar mass or to measure a pressure differential off of low concentration solutions, it becomes really easy to do things like figure out the molar mass of a compound based upon how that solution behaves. Now we can do this same kind of calculation with freezing point and boiling point changes as well. In lab yesterday, you did this with freezing point, where you used freezing point data to work your way backwards from molality to molar mass. But we're going to focus on osmotic pressure because it's probably even more common to do this, just because all you need to do is have a small amount of sample, dissolve it in water, measure its osmotic pressure, and you can work your way backwards to figure out what the molar mass of that substance is. So let's take a look at an example. Here I have 47 milligrams of a water-soluble non-electrolyte isolated from a South African tree. The sample is dissolved in enough water to make 2.5 milliliters of solution. And the osmotic pressure is 0.489 atmospheres at 25 Celsius. We want to know what the molar mass of the compound is. Okay, lots of information in this problem. But again, the big takeaway here is, look how much material we had to use to get this. 47 milligrams of this sap or whatever, and 2.5 milliliters of solution. So practically nothing. And yet it's still generated nearly half of an atmosphere of pressure on its own. So setting it up, pi, osmotic pressure is equal to the Van Hoff factor times molarity times R times T. The molarity here, or excuse me, the osmotic pressure is 0.489 atmospheres. We're told that this is a non-electrolyte. When we see the word non-electrolyte, our first instinct should be I is equal to 1. Now, we don't have enough information to know the molarity yet, so I'm just going to leave that variable alone. Our R value, since we're in atmospheres, is going to be 0.0821 liter atmospheres over moles times Kelvin. And 25 Celsius is 298 Kelvin. So to get the molarity by itself, I'm going to have 0.489 atmospheres divided by 0.0821 liter atmospheres over moles times Kelvin and 298 Kelvin. Canceling out our units, atmospheres come away, Kelvin go away. We have 1 over liters over moles. So reciprocal of that would be moles over liters. So we are going to get molarity at the end of this. Let's just figure out the number. 0.489 divided by 0.0821 divided by 298 to 3 significant figures. 0.0200 molar is our molarity here. Now, to figure out molar mass, I need to know grams of the compound divided by moles of the compound. Well, the grams of the compound I already have. 47 milligrams would be 0.047 grams. For the moles of the compound, I know its molarity, and I do know the amount of solution. Molarity times volume would be moles of the solute. So 2.50 milliliters, I need to turn that into liters. And 1 liter is 0.02 moles. So 2.5 times 0.02 divided by 1,000. 5.00 times 10 to the negative fifth moles. So now I have the moles. Grams divided by moles will give us molar mass. So 0.047 divided by 5 times 10 to the negative fifth. Two significant figures. It'd be 940 grams per mole. This kind of analysis could then be paired with other kinds of analyses to try to isolate what the compound actually is. All right, questions here. All right, try this next top hat question then. Of a similar kind of framework, I have an aqueous solution made by dissolving 11.9 milligrams of a non-electrolytic protein in enough water to make 4.88 milliliters of solution. If the osmotic pressure is 523 millimeters of mercury, what is the molar mass? Just one note here to help you get moving. Since we are dealing with millimeters of mercury, we're going to want to deal with the other gas constant. All right, go ahead and try this one. All right, let's try to figure this out if we haven't got it yet, or at least check our answer. So basically, the structure is pretty much the same here. Pi is equal to IMRT, which again, non-electrolyte means I is equal to 1. We don't know the molarity yet, don't have all the information to solve for it, so we're going to leave it there as this 62.36 millimeters of mercury times liters over moles times Kelvin. And our temperature here, as we've been doing kind of as a default, if we are not given a temperature, standard condition 298 Kelvin generally applies. And all of this is equal to 523 millimeters of mercury. So solving for M, we're going to divide the 523 by the 298 Kelvin and the 62.36. So 523 divided by 62.36 and 298. We're going to get a molarity of 0.0281. And that molarity is moles of protein over liters of solution. So if I multiply that by the volume of the solution, 4.88 milliliters, or 0.00488 liters, I get 1.37 times 10 to the negative fourth moles of protein. Molar mass is grams over moles, so 0.0119 grams divided by 1.37 times 10 to the negative fourth moles. And we get 86.6 grams per mole. All right, any questions here? All right, so that's pretty much the last colligative property question. Before we put solutions away fully, just a couple other things I want to talk about that were just of interest. We started this chapter talking about colloids, or at least mentioning the existence of colloids, these heterogeneous mixtures that appear to be all mixed up, but aren't truly mixed at the atomic level, at the molecular level. And these are interesting because they expand into a lot more areas than we actually think. When it comes to colloids, most of the time, most people will focus on one particular colloid, and that is the emulsion. And the reason we think about emulsions is because that's probably the one that we encounter the most. Milk is a fantastic example of an emulsion. Through the processing that goes into taking milk from the cow to your table, there is stuff that goes on that emulsifies it, makes it look like it's just one solid thing. Well, one liquid thing. But in reality, what you have is just a very fine dispersion, microscopically, of the fat globules and proteins that make up the milk in their liquid medium, but it's not truly a homogeneous solution. It's been homogenized to look uniform, but it isn't actually uniform itself. But if we look at the list here, you can see there are a lot of examples of substances that actually are colloidal in nature that are not true solutions, even though they kind of look like it. So, for example, smokes and fogs. They are a classification of colloids known as aerosols, and they are the kind of mixture of either gases in liquid, in the case, let me rephrase that. For a smoke, it's actually solid dispersed in gas. And you know this, you go to a bonfire and you see the smoke coming off of it. There's ash in there, there's soot in there. Put anything of, you know, anything white in kind of the mixture, you're going to see it's going to get that kind of ashy, sooty appearance to it. But fog, you go driving on a humid morning and you got fog kind of resting over the road. That's an emulsion, or excuse me, that is a colloid. The particular colloid here is an aerosol, but the liquid phase is water being dispersed in the air. Foams, like soap bubbles. Um, Solid foams like aerogels or um, things like polyurethane foams, things that make up seat cushions. Um, those are colloids. They're mixtures of gas dispersed through a solid medium to make the solid feel less, well, hard solid. So lots of different kinds of colloids exist, and they take over a lot of things that we encounter kind of normally. The other thing that I wanted to make mention of are surfactants. Surfactants are another really kind of interesting zone that solutions can live in. And what's really cool about surfactants is that these are molecules that have the capability of interacting strongly with both polar and nonpolar media. So they kind of live in that space between. We talked about like dissolves like. Well, this is a kind of substance that likes everything. It can be hydrophobic and interact with organic molecules and grease molecules and those kinds of things. It can also be hydrophilic and interact with water and water-based solvents. A great example of this is the compound sodium laurate. Now, where have you heard of sodium laurate before? Have you heard of sodium laurate before? Or maybe it's close cousins, sodium laureth sulfate, sodium laureth chloride. Ever read the ingredients on the back of your shampoo bottle? Okay, go home and try it. You're going to find these kinds of compounds in there. These are found in a lot of soaps, shampoos, and the reason they're there is pretty simple. The stuff that usually makes you smell bad isn't stuff that just gets rinsed off with water. Your body products are organic. Organic compounds don't dissolve terribly well in water. So how does your body compensate? Well, your body compensates by, we use soap to help us to remove those agents from ourselves, because the big hydrophobic end goes out and attaches to the grease, attaches to your sweat, attaches to whatever else is coming out of your body just during the normal course of the day that makes you smell bad, and you come out of the shower smelling great. And so this is how soap works. This is what soap does. Um, and so, surfactants act as detergents in a lot of cases. Um, and when you see compounds, um, this is basically what they're doing. The soap molecule penetrates the molecule of grease or dirt or whatever, puts all the hydrophobic tails in to attach itself to that molecule. That leaves the hydrophilic ionic end sticking out. That's the stuff. That's the part that dissolves in water, and it goes down the drain. So let's stop there and take a break.